The chart that you see in front of you is a chart of all the representative elements. So remember, this is groups 1A through 8A. That includes the noble gases right here that I'm showing with my cursor. And it's excluding the transition metals, which would be right here. This chart is showing what we call Lewis dot structures. And Lewis dot structures show the outermost electrons in the outermost shell of each atom, and these are called the valence electrons. And so we can notice that the valence electrons are shown, and there can be a maximum of 8 of them, as we see here in the noble gases. And when we start drawing a Lewis structure, for instance, we'll look at sodium in group 1A, we just have 1 electron in the outermost shell. Magnesium has 2, and notice that the second electron is put opposite of the first one, and that's to balance those negative charges. Aluminum has 3, silicon has 4. When we move on to phosphorus at 5 electrons, we can begin pairing them up. So when we draw Lewis structures, we first draw the electrons as single electrons, and you can think of them as on the sides of a square, as we do in silicon. So we have 1, 2, 3, 4 electrons, and then we can begin pairing them up. As we discussed before, elements want to follow the octet rule. Okay? Atoms want a full outer shell of electrons. They want to have the configuration of a noble gas. They want to be like noble gases. Well, how does this happen? Well, in this tutorial, we're going to just be focusing on metals, and they're shown here in light blue on this chart, and nonmetals, which are shown in yellow. And let's take the example of sodium. Sodium has 1 electron in its outer shell. And in order to have a complete outer shell, it needs to lose that 1 electron. Chlorine has 7 electrons in its outermost shell. So in order to have a complete outer shell, in order to fulfill the octet rule, it needs to gain 1 electron. So what can happen with sodium and chlorine is that sodium can give its 1 electron to chlorine. And in the process, what's going on here is that sodium becomes the sodium ion because it's transferred this electron to chlorine. Chlorine is gaining an electron, and it's becoming the chloride ion. These two are bound together by electrostatic forces, meaning that positive charges are attracted to negative charges. And that binds the 2 ions together as sodium chloride. This is an ionic compound. Ionic compounds, oops, woo, look at that. Metals, or a metal plus a nonmetal. So here sodium is our metal, chlorine is our nonmetal. The metal forms a cation, the nonmetal forms an anion when the electrons are transferred. So an ionic compound is a metal and a nonmetal. And bonding occurs by the transfer of electrons. So, okay, there we go. If we take a look at the 1A elements, okay, the group 1A elements, they have 1 electron in the outermost shell. The group 7A electrons have 7 electrons in the outermost shell. So therefore, in ionic bonding, oops, let's get a pen going on here. In ionic bonding, 1A metals bond with 7A nonmetals, sorry, in a 1-to-1 ratio. And you saw my prior example with sodium and chlorine making sodium chloride. We can also look at potassium, which has 1 electron in its outermost energy level. And bromine, which has 7 electrons in its outermost energy level. Potassium will transfer its lone electron to bromine, making the bromide ion. And this becomes potassium bromide. This is the ionic compound. There's the formula. It's in a 1-to-1 ratio. 1 part potassium to 1 part bromine. The name of the compound is potassium bromide. Okay, the compound ends in IDE. So if we look at all the 1A elements, lithium, for instance, could combine with fluorine to make lithium fluoride. Rubidium could combine with chlorine or any other 7A element to make rubidium chloride. So these are ionic compounds made of 1A metals and 7A nonmetals. Likewise, 2A metals bond with 6A nonmetals in a 1-to-1 ratio. So if we look at, for instance, magnesium has 2 electrons in its outermost energy level, okay? And sulfur has 6 in its outermost energy level. So magnesium needs to give up these 2 electrons to have an complete outer shell. Sulfur needs to gain 2 electrons to have a complete outer shell. So the 2 electrons in magnesium can be transferred to the sulfur. Okay, and in doing that, we make magnesium sulfide. Whoops, problem there. That's okay, we'll just leave that there for your entertainment. In this process, magnesium has lost 2 electrons. So magnesium has become magnesium plus 2, the magnesium ion. It's lost these 2 electrons. These 2 electrons go to sulfur. And sulfur gains these 2 electrons. These 2 electrons here are coming from the magnesium to make the sulfide ion. Okay, so these 2 electrons here are the electrons here that are added on to sulfur to make the sulfide ion. So notice that we have a +2 charge here on the magnesium ion and a -2 charge on the sulfide ion. And that is what creates the electrostatic charge that bonds the two ions together in the ionic compound magnesium sulfide. What if we have magnesium, 2 electrons in the outermost shell, and we have fluorine, which has 7 electrons in the outermost shell? How could they combine and form an ionic compound? Well, magnesium needs to lose these 2 electrons to have a complete outer shell. Fluorine needs to gain 1. So one of the electrons can be transferred from the magnesium to the fluorine to make the fluoride ion. But we still have 1 electron left here. What needs to happen in order to make a compound here between magnesium and fluorine is that we need another fluorine atom. Okay? And that fluorine atom will be able to accept that other electron that's in the outermost energy level. So the magnesium transfers both of its electrons. In the process, it becomes magnesium ion. Okay? And those 2 electrons go to fluorine. 1 fluorine atom takes an electron to make the fluoride ion, and a second fluorine atom takes the second electron to make the fluoride atom. And this becomes magnesium fluoride. Since there's 2 fluoride ions here, 2 fluorine atoms, each had to take an electron to become the fluoride ion, we need a subscript of 2 here. So the ratio is 1 to 2. 1 magnesium to 2 fluorines to make magnesium fluoride. So what I've shown is how the ionic compounds have formed via the Lewis dot structures. There is an easier way to do this. We can write the formula for any ionic compound if we know the charges of the ions. So, for instance, we know that in group 1A, these form ions with a +1 charge. Group 2A metals form ions with a +2 charge. Group 3A metals form ions with a +3 charge. The group 4A metals, tin and lead, form ions with a +4 or a +2 charge. Group 6A form anions. These are nonmetals with a -2 charge. Group 7A nonmetals form anions with a -1 charge. We're going to leave group 5 alone for right now. Okay? And of course we know that the noble gases do not form ions, so they would have a 0 charge. Let's say we wanted to form ionic compound with aluminum and bromine. The first thing that we want to do is take a look and see what the charges of the ions would be. The aluminum ion, it's in group 3, would have a +3 charge. So let's write the charge right there. And bromine has a -1 charge. Okay, remember that when ions have a +1 or a -1 charge, we can either write plus or just minus. We don't have to write the 1, the actual number 1. Okay. So since aluminum has a +3 charge and bromine has a -1 charge, in order to make an ionic compound, the charges have to balance. That means that they have to equal 0. Our positives plus our negatives have to equal 0. So right here we have 3 positives, we have 1 negative. In order to get the charges to balance, for every aluminum, we need to have 3 bromines, or 3 bromide ions. Because this would equal this total charge here Since now there's 3 would equal a total net charge of minus 3. The net charge on aluminum is plus 3, and therefore the charges balance. So that's how subscripts arise in formulas for compounds, specifically ionic compounds. There is a shortcut way of doing this. We can use what we call the crisscross method. And in the crisscross method, what's going on, and let me change colors here, is that the charge on the cation becomes the subscript on the anion, and the charge on the anion becomes the subscript on the cation. They are crisscrossing. So the charge on aluminum is 3. That 3 crisscrosses and becomes the subscript for the anion. The charge on the bromine was 1. Okay, that 1 is a subscript on the aluminum, and when subscripts are 1, we don't write them. Let's look at some other examples. Let's say we have calcium combining with oxygen. Calcium's charge would be plus 2 as an ion. Oxygen's charge would be minus 2. If we use the crisscross method, this 2 becomes the subscript over here. This 2 on the anion becomes the subscript over here. So we end up with Ca2O2. But since both of these subscripts are 2, we can simplify this and make this just CaO. In an ionic compound, the subscripts are at their lowest whole number ratios. So 2 and 2 would simplify down to 1 and 1. The name of the compound would be calcium oxide. Okay, we can take a look at another example, and let's try potassium and combining with sulfur. Potassium is in group 1A and want to have a plus 1 charge. Sulfur is in group 6A and has a minus 2 charge. So if we use the crisscross method, the charge of plus 1 would be the subscript on sulfur, and the charge of 2 here would be the subscript on the potassium. So our formula would be K2S, and its name would be potassium sulfide. If we let's take another example. We'll combine strontium with bromine. Strontium is in group 2A. It has a plus 2 charge. Bromine is in group 7A. It has a minus 1 charge. When we employ the crisscross method, the 2 becomes the subscript on the bromine. The 1 becomes the subscript on the strontium. So our formula is SrBr2, and the name of our compound is strontium bromide. So we can see that we have something in common with the names. The names of these ionic compounds all end in IDE. They start with the name of the cation. So the cation here is calcium. And they end with the name of the anion ending in IDE. So calcium oxide. Calcium's the cation, oxygen's the anion. Potassium sulfide. Potassium's the cation, sulfur's the anion. Strontium bromide. Strontium's the cation, bromine is the anion, or bromide is the anion. The charges have to balance. The crisscross method is the shortcut way of ensuring that, but we can go and double check our formulas to see if those charges balance. Calcium has a +2 charge, oxygen has a -2 charge, +2 and -2 balance. Potassium has a +1 charge, sulfur has a -2 charge. We have 2 +1s, that equals a +2 net charge here on the cation, a -2 charge on the anion, the charge is balanced. Strontium has a +2 charge, bromine has a -1 charge. There are 2 bromide ions, anions, so that is a net charge of -2 on the anion side, and a +2 charge on the strontium side. +2 and -2 equals 0. The charges balance in this compound. So that remember that in these compounds, in the ionic compounds, the charges must balance. The charge of the cation plus the charge of the anion has to equal 0. And we can see that.